Hello, my name is Samantha Wismer. I am a recent graduate of the University of Pittsburgh's Department of Mechanical Engineering and Material Science, and I am here to present the integration of computational fluid dynamics into an introductory mechanics course. When looking toward upper-level engineering courses where the subject matter becomes more abstract, the need for integration of a laboratory component to the course curriculum becomes more apparent. Collegiate courses that lack this laboratory component also lack the opportunity for experimental learning. This deprives students the ability to introspectively question established paradigms, convert their short-term memory into long-term memory, and to be actively engaged in their learning via partner and group activities. Of the reasons for not including a laboratory component into a curriculum, most center around cost and resources rather than any lack of benefit to student learning. However, using a simulation software to replace a physical lab component to a course simultaneously allows for experimental learning and exposure to a software commonly used in industry. To build upon our prior research, we decided to implement ANSYS CFX in an introductory fluids mechanics course. The software was introduced as students were learning the Navier-Stokes equation and was used in multiple assessments and exams. In order to understand student interest in the software, as well as whether utilizing the software had any impact on how students felt they understood the subject matter, a survey was presented before and after the software was used, and resulting responses were coded according to Creswell's coding scheme. The first question students were asked in the pre-survey gauged whether or not they had been exposed to computational fluid dynamics in the past. An overwhelming majority indicated that they had not had any exposure to the software, and of the students who did, many claimed to be self-taught. This established a need for teaching computational fluid dynamics at the undergraduate level. Even though students have not had exposure to computational fluid dynamics, it does not mean they are ignorant to its significance. When asked how they feel about using ANSYS CFX in the classroom, 15% of respondents recognized that learning this software would provide them a skill set useful in their later careers. On the left, we see the codes assigned to each student response and their corresponding definitions. On the right, we see the percentage of student responses that received each code. It is noted that responses with a positive connotation are highlighted in green, those with no connotation highlighted in yellow, and those with a negative connotation highlighted in red. This scheme will remain consistent for the rest of the presentation. The fact that students understand the impact learning a widely used software can have on their life after graduation was showcased earlier in Bruselli's research. Additionally, almost a third of students indicated a strong interest in using the software, and those that did not largely either were neutral to the introduction of the software or expressed concerns of the software being too difficult. I do not know whether this is due to a stigma around the software or just pure ignorance of how it is used. When asked what they hoped to be able to do with ANSYS CFX after completing the course, a spread of positive responses ranged from being able to apply the software to projects both in and outside of the classroom to simply gaining a new set of technical skills. As shown by the bottom response, some students have a clear direction of their career path and have a desire for knowledge that will help them in their journey. A large amount of students admitted that they did not know what the software was capable of and therefore did not understand what they should be expected to do with it. This is unsurprising considering 93% of students had no previous exposure to computational fluid dynamics. At the end of the term, after the students had the chance to learn and use ANSYS CFX, they were asked if the ability to visualize fluid flow had any impact on their understanding of fluid dynamics. A majority of students indicated the visualization aspect of the software had a positive impact on their understanding. They were able to vary the boundary conditions to see how the fluid reacts instead of just comparing different numeric results that may mean nothing to them on their own. Even just seeing the fluid flow provided students the physical context they needed to better understand what was being taught in the classroom. As mentioned in CERT's research previously, the difficulty in understanding abstract concepts can discourage students. Providing context and visual representations remedied this frustration. Of the negative responses we received, a good amount of them revolved around difficulties using and accessing our university's virtual lab. This online application allows students to remotely access university computers and the applications therein. Plans to implement ANSYS CFX in future courses will definitely involve a remedy to this issue. Next, we aim to see if the use of the software improves student abilities to problem solve. Many students indicated that solving problems by hand and having ANSYS verify their results improved their confidence in their problem-solving abilities. It is interesting they made note of this, as they could get the same satisfaction of being correct by simply referencing a solution guide. It is wondered whether the final result coming from ANSYS has more significance in student minds than those that come supplied by their professors. Additionally, students began to understand what kinds of answers they should expect of a problem given the situation. This is something a lot of young engineers struggle with, determining what is a reasonable answer. Through using ANSYS and knowing what to expect, students were able to more easily recognize if they had made a mistake somewhere in their work. Students also mentioned how comparing their results to the results in ANSYS typically allowed them to identify where they had made an error. On the flip side, some students found the program to be difficult to understand, kind of like a black box that spits out an answer without any rhyme or reason. This is an issue researchers see being remedied by spending more time on the theory of CFD as the software is introduced. In post-survey question 3, we asked students if they enjoyed using the software and why. Many students did enjoy using the software in the classroom. Some harped back to the point made earlier that being introduced to a software commonly used in industry brings a practicality to the classroom, and they see a direct benefit of what they are learning. Other students saw a benefit to their education. Having to use the software to resolve a problem provided another opportunity for exposure to the material within the problem, as well as the opportunity to visually see the solution. Interestingly enough, some students found learning and using the software fun. They felt it broke up the monotony of the classroom. As a student, I understand this and see the importance of breaking up the curriculum with something that is still beneficial to student learning but also boosts morale. Again, as seen previously, technical issues made the experience using the software a negative one for many students and unfortunately hindered their learning of the software and gaining benefits from its use in the process. Finally, we wanted to know what we did right in the software's implementation and what we did wrong. While we did align the introduction and instruction of the software well within the course content, we did not spend enough time using it. These results give us a good direction in terms of restructuring the curriculum to better fit in CFD theory and the application of ANSYS CFX in a way that best aligns with course content. We want students to not only gain a better understanding of the material, but also a skill set that will help them as they continue into their future careers. Responses indicating that 93% of students had no previous exposure to computational fluid dynamics establishes a need for the theory and softwares that implement it to be taught. Additionally, students want to learn this software. They are excited and open to the possibilities. Those that are nervous about doing so likely have reservations due to their own ignorance of the software and how to use it. After using ANSYS CFX, student responses were largely in the positive. They were able to contextualize what they were doing. Students often do not have everyday exposure to fluid flow and therefore have very little physical reference to what they are learning, and that can lead to issues understanding fundamental concepts. They were better able to problem solve by being able to predict outcomes and determine if they were reasonable, compare their solutions to ANSYS to find their mistake, and to be confident in their final answer. They know as much as we do that understanding simulation software will hugely benefit them in their careers, as the engineering world has largely gone digital. From this survey, we also now understand the need to implement ANSYS sooner and mitigate problems with our university's virtual lab. In the future, we hope to implement computational fluid dynamics again and objectively and subjectively quantify by how much it benefits student learning. Again, my name is Samantha Wismer, and I want to thank you for your time and attention in my presentation.